We're now going over to memory forensics, and specifically we're going to talk or learn about the heap. And I'm just going to introduce Christian Müller, who's going to join us virtually.
My name is Chris. I'm from Trufflepig Forensics, and I will talk a bit about the heap and our research around the heap. I will start with a short introduction, then talk about version stability and why we even do that, demonstrate parts of the work, and give an outline of what we still have left to do. And I can already say this is a pretty early stage research, so there's a lot left to do. Yeah, as I mentioned before, my name is Chris. I'm one of the co-founders of Trufflepig. We are doing memory forensics. So also this research is in the domain of memory forensics. And in memory forensics, you have the problem that was mentioned before in the SSH talk, that data structures are changing from version to version. And in memory, as memory itself is volatile, also the data structures are pretty volatile from version to version, as you don't need to worry about adjusting the parser or anything. So one version may look completely different than the other one. For example, in the Linux kernel, there you have even in the compile time an option to randomize the structs in the kernel to prevent some sort of exploitation techniques. Yeah, and we are trying to get version stability also in Windows. So right now we are focusing on Windows forensics, memory forensics, and also in the userland. And as we are just starting out with userland analysis, we've started taking a look at the userland heap, namely the NT backend heap, which is a first heap implementation from Windows. I won't talk much about that because there's more interesting things to tell you. Yeah, a bit about version stability. So when you want to find out how the data looks in memory, you can either reverse engineer the same thing every update and try to make sense of the offsets and get the information in a profile. If debug information is available, you can also use that. But so for example, for memory forensics profiles, that's a common technique for Windows, as they do give out some debug information for the kernel that you can retrieve a lot of information from. But sometimes it also takes a long time until you get that information for a new kernel, up to several months. So it is good to have alternatives to that. Yeah, so a better practice to get new offsets and information on where data is located in memory is pattern scans. So you basically reverse engineer the source code, try to find references to the structures that you're interested in. And with those references, you try to find patterns that are version stable for those code segments accessing the data that you're interested in. That works relatively well. So you can have like 10 patterns, and you will match that the data structure that you're looking for, the offset or the global symbol, in like 10 versions or maybe even 15 versions. And then you sometime need to add new patterns to find it also in new versions. Then you can also use, of course, live analysis, not just like taking a look at the binary itself, but also do it in live memory. Try to introduce known values in memory. As an example, in the implementation in the Windows kernel for networking is completely undocumented. There are no debug information available. There is some reverse engineering work related to that, and yeah, it's pretty good, but there are some things missing, especially for newer versions. There are some offsets missing, and it helps to start an application that you know which port it will use, and then just scan for that port in a range, and you will pretty quickly identify that port, and you will be able to update that specific offset. There are other offsets that you may also be able to write heuristics for. Like, for example, it needs to be a pointer. It needs to point to a data structure that is a valid string, things like that, which works surprisingly well. I didn't expect that, to be honest, but with those kind of rules, just applying 7, 8 of those rules, and you have a pretty stable heuristic for an offset. Then, of course, an improvement to the pattern scans is emulation. So you just need to find a function, and you can emulate that function, and in the best case, you will get the offset that you're looking for. Then we've also heard today before that machine learning can help in certain cases to identify the layout of data structures. And in our case, we of course don't have the ability to do live forensics or have a live image that we can manipulate data into our needs. We just get a memory snapshot, and we need to make sense of it. So I will just give you a brief overview on what we did so far. So here we do have a memory snapshot, or an analyzed memory snapshot from my VM. I've started a process there. I can show you in a second. So there is a process called Heap test, started by PowerShell, and it does have 4 heaps. So we detect the heaps first, and we also parse the allocations on the heap, as I mentioned before. So we do parse the NT heap, and we get all the allocations on the heap. With those allocations, we can now take a look at them and scan for pointers, or in general, just scan the whole stack, the whole heap data structure, heaps in the. So there are, when you take a look at the memory regions, sort for type. There are multiple heaps in here, a stack. The files are not really interesting, and the shared libraries may be interesting. The unknowns, we will just strip them out. So we can scan for all pointers in those 3 different types, as we may have global symbols in the shared libraries. And then we can further identify the allocations. There might be pointers in the middle of the allocation, so that we have an indication of maybe double linked lists in C. They may not point to the begin of the structure that we are looking at, but in the middle. That's pretty common in the in kernel in the kernels. And we may find, if we are really lucky, we may find allocations with RTTI information or virtual function tables to begin with, and if we are really lucky, then find RTTI information on those classes. So we and associate the pointers to those allocations as xrefs. So we can directly see, okay, there are references to those class instances, and we can just fill them in and get more information about them. So in this case, I've written a small test program. This is basically my own very, very tiny game engine with 200 lines of code. So we have teams, as you can see here, player, we have weapons, objects, and they are allocated on the heap, and they do have that virtual function table. And as this is not a very nice way of visualizing that data, I've started implementing a graph for that, so we can see there are objects with an address that are of the type visualized here. So here you can see, okay, we have 2 objects in the game, 3 players, 1 team, and 6 weapons. So unfortunately, we don't have the xrefs visualized here yet. But once we have, you will directly see from that graph that the players have references to weapons, and each player has 3 references of to a weapon, but 2 references to one of the weapons, which then indicates, okay, there might be 2 pointers indicating that there is a primary and secondary weapon, and the third pointer shows or indicates the current weapon the player has selected. With a team, we do have a problem here. I did not check yet what the problem is, because there should be 2 teams. But apart from that, this already looks pretty good. And yeah, as I said, with more references between the artifacts, we will also gain a way better and quicker insight into what's going on there. We will also add in the future references from the stack, for example. So there is another object missing here, which is the world. The world is on the stack, so we can't see it here because those are only the allocation ones, and the stack is not yet an allocation, so it's not scanned in our data structures. So yeah, and we need to add that. We've tried to add all those references in the beginning, but it was pretty overwhelming. There were, I think, around 800,000 or up to 800,000 pointers per application. And trust me, you don't want to wait that long until they are inserted into the database. So we stripped it down to the bare minimum, and yeah, this is basically the current state, and we also want to achieve that we get those information from kernel allocations, so not only from the anti-heap, but also from pool information or pool allocations, the small and the big allocations at the kernel. They also indicate the type. So there is, we can take a look at that here. We have Windows kernel object type. There are several of those types, and they also have a pool tag and an index, and we can look those up in the pool tags and the pool allocation headers. So there's also the index to the type. So we can try to auto match an object type just by examining the pool allocations and make sense of it without knowing the data structure before. So for a process, I mean, that's already in the product, also in other products, but for other types and how they are interconnected, just getting that mesh of pointers visualized is what we think will really bring value into reverse engineering not only heap data or userland heap structures, but also kernel-land heap structures. And yeah, that's pretty much it for now. I hope you liked it, even though it was pretty early research. And yeah, thank you for your attention. I'm open to questions.
Yes, thank you very much. So again, I'm looking around to see if there are any questions right here. No, there are not. Any in the chat? No, they're not. So I got a question for you. So what interests me right now is, have you used this approach like on any applications so far to extract some forensic evidence, or is that yet to come?
Yeah, so we started taking a look at that with very basic things like Notepad. And what we were able to get is, the text that is in Notepad visible, written at the moment. And that is a pretty simple pattern to detect. So you get an allocation that contains text, or UTF-16 encoded text, and it has one reference, and then you will only get that one single single result with the actual text of Notepad at the moment. So this was the first proof of concept that we did, which worked pretty well. And yeah, I think that's also version stable from one Notepad version to the next. And yeah, we just started with some students to work on browser artifacts. And one of the really interesting projects that I'm looking forward to is information from Tor, so that you get the routing information from the Tor memory, and also potentially the domains, the onion domains that you're connected to at the moment.
Okay, sounds like a plan. Great. Thank you very much. If there are no other questions? No, there are not. Yeah, thank you again.